In this video, we introduce the idea of an antiderivative of a function, and we work a couple basic examples. Then we take a moment to discuss the most general form of an antiderivative, and we introduce the indefinite integral notation for a general antiderivative. Next, we show that antiderivatives, in other words, indefinite integrals, work across linear combinations of functions. And finally, we work several examples of computing indefinite integrals with linear combinations. So we kick things off with a definition for an antiderivative. We normally use a capital letter for that if the original function has a lowercase letter. So capital f of x is an antiderivative of little f of x on some given interval I, if the derivative of capital F of x is equal to the original function, little f of x. So we're just trying to find the function that differentiates to the given function. This is best explained by example, and we have two short examples here. In the first one, we're asked to find two distinct antiderivatives of this function, little f of x equals 2x. So we're just trying to guess something that differentiates to 2x. And just using the power rule here, we can guess pretty quickly that capital F of x equals x squared is one valid solution to this, because if I differentiate it, that's the derivative of x squared, and I use the power rule on this, I bring down a 2 out in front, and then I subtract 1 from the exponent, and I end up with the 2x that I started with. And this brings up an important side note. You can always check that your antiderivative is correct by simply differentiating it to make sure that it works. So big F of x equals x squared is one solution to this thing. But we realize there are more solutions than this because the derivative of an additive constant is just 0. So for example, big F of x equals x squared plus 1. That also works because the derivative respects linear combinations. So if I take the derivative of this combination x squared plus 1, that means I just take the derivative of each piece of it separately. I'm going to use Leibniz notation here to show how the derivative distributes to each of the terms. So the first derivative of my proposed antiderivative is given by the derivative of the first piece, that's the x squared piece, plus the derivative of the second piece. That's the constant 1. And we remember the derivative of a constant vanishes. And I'm just left with the derivative of x squared again, which is 2x. And so we found a second function that differentiates to 2x. So that's the flexibility that comes with antiderivatives. We always have this additive constant flexibility where you could add in any constant that you want and find a new antiderivative. In our second example, we want two distinct antiderivatives of f of x equals x squared. And so again, this is kind of a guess and check process, or if you like, what we're doing here is using the power rule backwards. I know that the antiderivative here essentially comes from x cubed. But if I differentiate x cubed, it would give me a 3x squared instead of a 1x squared. And so all I have to do is make an adjustment out in front with a factor of 1/3. And now this thing is set up so that the derivative comes out to the original function x squared. Just to verify that it works, compute f prime of x. The derivative sees right past that constant multiple, so the 1/3 is a spectator here. Then I need the derivative of x cubed, so I bring the power of 3 down in front, subtract 1 from the exponent. My 1/3 was cleverly set up to cancel the 3, and I end up with the derivative being x squared. And again, that verifies that the function capital F of x equals 1/3 x cubed is the antiderivative of x squared. Now we've already learned our lesson about how to find additional antiderivatives. We have this additive constant flexibility, so we can add whatever constant we want to this, and it will also be an antiderivative of the original function. Just to keep it interesting, I'm going to make that constant pi this time. Pi is just a constant, so when I differentiate this new capital F of x, I get the same result. It's just x squared. So antiderivatives come with the flexibility of an additive constant simply because the derivative of a constant is 0. What we want to accomplish now is to show that given a capital F of x, that's the antiderivative of a little f of x, capital F of x plus an arbitrary constant is the most general antiderivative of that little f of x. And there's two different pieces to this. First, we want to show that capital F of x plus c is also an antiderivative of f of x. And second, we want to show that any antiderivative of f of x is expressible as an f of x plus c. Those two facts put together allow us to call f of x plus c the most general antiderivative of little f of x. And then in part 3 here, we're going to introduce a new notation for the most general antiderivative of little f of x, and that's called the indefinite integral. So again, we start out this theorem by saying, let capital F of x be an antiderivative of little f of x on some interval I. And then part 1 here is the claim that capital F of x plus c is also an antiderivative of little f of x. And the proof of this is really quick. All we have to do is show that the derivative of this proposed function comes out to little f of x. So let's differentiate it. We remember that derivatives respect linear combinations, so that derivative applies to each term separately. So we get d dx of f of x plus d dx of a constant, which again vanishes. So the constant part is gone, and I end up with just the derivative of capital F of x. But we started with the assumption that capital F of x is the antiderivative of little f of x. In other words, it's the thing you differentiate to get little f of x. So we're done showing that f of x plus c is also an antiderivative of little f of x. Now the second part's a little more tricky to prove. I want to show that for any antiderivative of little f of x, there exists a constant c that allows you to express that antiderivative as capital F of x plus c. In other words, all antiderivatives are related by additive constants. So our two assumptions here are that capital F and capital G are both antiderivatives of f of x, and this means their derivatives are equal to little f of x. Just to summarize that fact real quick, big F prime of x is equal to f of x, and big G prime of x is equal to f of x. Now, how do we show these two functions are related by an additive constant? The trick to this is to introduce a new function given by the difference of these two functions. So we're going to say let h of x equal the difference big G of x minus big F of x. Then we apply the derivative to both sides of this, and we end up with h prime of x. And again, differentiation respects linear combinations, and I get G prime of x minus F prime of x. Now the payoff here is to realize that G prime and F prime are both equal to little f of x. And f of x minus itself is simply 0. And so I've arrived at this fact that h prime of x is equal to 0. Well, any function that differentiates to 0, as it turns out, is a constant. So I've showed that h of x is equal to some constant, and I'll call that c. And this means if I go back and look at my original definition of h of x, this means that the difference g of x minus capital F of x is equal to some constant c, which in turn shows that capital G of x is expressible as capital F of x plus an arbitrary constant. So to summarize what we've accomplished so far, adding a constant to an existing antiderivative just creates a new antiderivative. And secondly, given any antiderivative for a function, any other antiderivative of that function is expressible as the first antiderivative plus an arbitrary constant. So this expression, capital F of x plus c, is the most general antiderivative of our little f of x. And we introduce a special notation for this called the indefinite integral. And the motivation for this actually comes from thinking about areas bounded by curves and what's called the Fundamental Theorem of Calculus. And I'll post a link to the video where the Fundamental Theorem of Calculus is derived. But for our purposes right now, this notation of an integral sign and then the function little f of x and then the dx after that, this notation simply means give me the most general antiderivative of little f of x. And so that's a function capital F of x that differentiates to little f of x plus an arbitrary constant. Now the last main point that I want to make in this video is that antidifferentiation respects linear combinations. And then we're going to use that fact to wrap things up with a couple more examples. So the statement of this theorem is that we have two functions that are antiderivatives of two other functions. So capital F is the antiderivative of lowercase f, and it's the same for capital G and lowercase g. A and B are constants. And what we're looking at in this indefinite integral notation is the antiderivative of a linear combination of these two functions, little f and little g. So a linear combination is just a sum of constant multiples of functions. And the way it's stated here is that the general antiderivative of a linear combination of these two functions is equal to the linear combination of the antiderivatives of those functions plus an arbitrary constant. And the reason this is true is simply because the derivative itself respects linear combinations. So to prove this fact, we just have to take the derivative of the thing on the right-hand side and show that it works. And I'll go ahead and throw the plus c in here, even though I know that piece is going to differentiate to 0. And so all we have to do to show that this expression is the antiderivative of af of x plus bg of x is take the derivative of it and show that it results in the original function a little f plus b little g. So we write down the derivative d dx of this expression, a big F plus b big G plus the arbitrary constant c. And we know that derivatives respect linear combinations. In other words, they distribute across sums and differences, and they go right past constant multiples. So we can re-express this as a times the derivative of big F plus b times the derivative of big G of x plus the derivative of the arbitrary constant big C. And of course, the derivative of an arbitrary constant is just 0. And by assumption here, big F was the antiderivative of the function little f. So differentiating it gives me the function little f. And I have a little f of x. And similar for g, the derivative of big G is little g, because big G is the antiderivative of little g. And by showing that the derivative of the right-hand side here is equal to the function a little f plus b little g, we've verified that it's the antiderivative. So this gives us a nice new tool in our toolkit for computing antiderivatives. I could summarize it by saying the antiderivative of a linear combination of functions is the linear combination of the antiderivatives of those functions. So let's apply this idea to our first example. I want the antiderivative of 3 cosine x plus 5. And we know that antidifferentiation respects linear combinations. So I just end up with 3 times the antiderivative of cosine. And you simply have to guess here, what do I differentiate to get the cosine function? Hopefully you remember that's just the sine function. And then I have my second piece. You could say we're looking for the antiderivative of 5. Or you could even say we're looking for 5 times the antiderivative of 1, whichever way you want to look at it. Well, the antiderivative of 1 is just x, so I have 5 times the antiderivative of 1, which is 5x. And then to be totally general, I put in the plus c. In the last example, I want the antiderivative of x squared plus 2e to the x. And again, we just split this up into terms. The antiderivative distributes across sums and differences and goes right past constant multiples. So I need the antiderivative of the first piece, the antiderivative of x squared. And we already covered this on the first slide today. The antiderivative of x squared is 1/3 x cubed. You could call that using the power rule backwards, or you can think of it as a guessing and checking and adjusting the constants out in front kind of process, whichever way you're more comfortable with. And then my second term is going to have a 2 out in front multiplied by the antiderivative of e to the x. Well, e to the x is the special function that's equal to its own derivative, so the antiderivative of it is just e to the x, because the derivative of e to the x is e to the x. We add in our arbitrary constant plus c, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.